So welcome, everyone. Great pleasure to have Stephen Jordan here. And also, as always, Hamoon Masuvi is kindly helping with all the moderating with the chat and questions. Okay, so Stephen is he's a quantum algorithms research at Google Quantum AI. He got his PhD in theoretical physics from MIT, and before joining Google, he was at NIST, Microsoft, and at the University of Maryland. He also, for a couple of years, he also served on an interagency working group on quantum information science for the White House Office of Science and Technology Policy. As you probably know, Stephen worked on a number of things, algorithmic problems, including adiabatic quantum computing, polynomial time algorithms for chemical dynamics, and algorithms for quantum field theories. He maintains this website called the Quantum Algorithm Zoo that catalogs all known quantum algorithms. So real pleasure, Stephen. Looking forward to your talk.
Thanks, great to be here. Let me pull up my slides. Are those visible?
Yeah.
Great. Okay. So I will talk about optimization by decoded quantum interferometry, which is joint work with Noah Schutte, Mary Wooters, Adam Zalkman, Robbie King, Sasha Schmidhuber, Sergei Isakov, and Ryan Babish. And this work is on the archive. And so if you want to see details, you can find them there. So the motivating question behind this line of work is whether quantum computers can achieve exponential speedup for optimization problems. And I think this has long been recognized as an enticing question because optimization problems have the right general characteristics for the possibility of exponential quantum speedup in the sense that these are big compute, small data problems. So more precisely, for many optimization problems, the number of computational steps classically needed to solve them grows exponentially with the number of bits needed to describe the problem instance. And this is a prerequisite it's sort of a necessary condition for exponential quantum speedup. Now, one thing to keep in mind is that many optimization problems are NP hard, so one doesn't expect polynomial time classical or quantum algorithms to solve worst case instances of these problems to exact optimality. And so what we instead ask is, can polynomial time quantum algorithms find approximate solutions that would require exponential time to achieve the same level of approximation using classical algorithms? And of course, the caveat is using known classical algorithms because you never know that maybe someone will discover something new in the future. And so this has long been recognized as I think, a really exciting problem. And many interesting approaches have been proposed, which made some progress on it, including the adiabatic quantum optimization approach and the quantum approximate optimization algorithm, QAOA. But I think it's fair to say that this problem remains largely open. And so in this talk, I'll give kind of a new line of attack on these kinds of problems. Although when I say new, of course, there are some historical precedents and intellectual ancestors of what we do, which is something that I'll go into in the first part of this talk. And so decoded quantum interferometry is very different from QAOA and adiabatic approaches because those both relate optimization problems to minimizing energies of Hamiltonians. So I do think it's very helpful to have some kind of physical intuition, some kind of physical phenomenon that's your point of contact between the behavior of quantum systems and the nature of the problem you're trying to solve. Hamiltonians are one natural choice, and the sort of the physical tendency for systems to minimize their energy. But here the point of contact is different. So what we observe is that cost functions of common optimization problems like Max-XORSAT, Max-KSAT, graph coloring, all these kinds of problems, they have, these cost functions have Fourier transforms whose wave vectors are very few and sparse. So these Fourier spectra are in a sense doubly sparse in the sense that there are very few wave vectors that have non-zero amplitude, and the ones who do are often in themselves sparse wave vectors. And in principle, there could be exponentially many non-zero terms in the Fourier spectrum, but there just aren't. And so we kind of try to exploit that and use a quantum Fourier transform to obtain constructive interference on those symbol strings where the objective function has larger magnitude and destructive interference elsewhere. And at the end, we can just measure in the computational basis, and we'll sample from some probability distribution over possible solutions. And this probability distribution will be biased towards solutions that are better. So in order to describe our algorithm, I should give some background on coding theory, some key concepts. And I won't go into any proofs, just sort of giving some concepts. And for some people, this will be review, but it will be brief. So consider a set of vectors in n-dimensional space, m-dimensional space, that is closed under addition and subtraction. So here's a illustration of that in 2 dimensions. And so if our underlying field is the real numbers, then this would just be the integer linear combinations of some basis vectors. And we'll mostly think, well, in fact, in this talk, we'll exclusively think about the context where the underlying field is a finite field. And in this case, instead of calling this object a lattice, we call it a code, but the concept is the same. So here's the formal definition of a given code. We have a matrix over this field, which is m by n, where m is bigger than n. And then the code is the set of vectors we get in the image of this non-square matrix B. And so there's a problem, the main computational problem in the context of codes, or at least one of the main problems, is the decoding problem. So we're given a point V, which is some vector in this space. I've drawn it here with this little red dot. And you want to find the nearest vector in the code. And you can think of your displacement from the nearest vector, or which we call in the context of coding theory the nearest code word. We can think of that displacement as being the error that we're trying to correct. And this is the decoding problem, which is NP hard in general. Now, there's 2 different ways you can kind of relax this problem to make it easier. So one way is to just ask for approximate decoding. So instead of finding the nearest vector, you just demand that you find a vector that is fairly near in some sense that you can quantify. And how near you demand it to be determines the difficulty of this problem. And by tuning that parameter, you can get to problems that are either still NP hard, or they can be still hard but not NP hard, or they can in fact just be easy problems that you know how to solve in polynomial time. And this is called the approximate nearest code word problem. A second way of making the problem easier is to add a promise. So you introduce the promise that the vector is close to the lattice. So you go back to demanding that you find the absolute nearest lattice vector, but if the point is far from any lattice vector, the algorithm is allowed to just say, I don't know, and give up. And this is called the bounded distance decoding problem, which I think is a very sensible name for it. And depending on what this promise radius is, this problem is also tunable between being NP hard and being NP and in between. For example, if this radius is only constant, then you could always just find the nearest vector by exhaustively searching all the points that are within that constant radius ball. But it also gets easier even beyond constant radius. And the last concept from coding theory / lattice theory is this notion of duality. So any code has a dual, and this is the set of code words that are orthogonal to all of the code words in our original code, C. So we call the dual C perp. And it is a duality in the sense that if you take the dual of the dual, you get back what you started with. And these two codes are related by a Fourier transform. In the case where our field is just the field F2, the bit, then that Fourier transform is really the Hadamard transform. And what I mean when I say these are related by a Fourier transform is that if you produced a superposition over delta functions at all the code words and you Fourier transformed it, you get a superposition over all the delta functions at the dual code words. And so here previously we've written down this matrix B, whose image is the set of all the code words. We can call that the generator matrix of the code C. The kernel of B transpose is the code C perp, and we call B transpose the parity check matrix of the dual code. So we just kind of interchange the roles of the generator matrix and parity check matrix to switch between a code and its dual. And so there's actually a long history of thought at the intersection between lattice or code duality and quantum computing, which goes all the way back to the early 2000s, that I'd like to summarize a little bit because it gives some geometric intuition of the ideas behind decoded quantum interferometry. And it's not really the way we originally conceived of it, and it's not really the way we presented in our paper, but it is an alternative way you can view our algorithm. So it really started with work in the early 2000s by Aharonov, Regev, and Tashma, which made the following observation. So I said on the previous slide that if you take a superposition over the lattice points or code words, then you Fourier transform, you get a superposition over the dual lattice points. But another thing you could say is, well, suppose we have a superposition over little peaks at each point on a lattice. That's shown on the right-hand side of this slide, instead of just delta functions. Now, if you take the Fourier transform of that, what you'll get is a weighted superposition according to some envelope function over the points in the lattice that's dual. And so that's shown on the left-hand side here. All these little blue dots are dual lattice points, and we've got some kind of Gaussian-looking envelope function weighting them. And so this was used in the early 2000s to obtain a bunch of reductions, quantum reductions between various lattice problems, which did not yield any algorithmic exponential quantum speedups, but it did yield a lot of insights into the hardness of these lattice problems, which then contributed foundations to the study of lattice-based cryptosystems. And more recently, there's been kind of a resurgence of activity in this area where some more algorithmic style payoffs have been obtained. Particularly, I'd like to highlight these papers by Chen, Liu, and Zhandry, Yamakawa and Zhandry, and Tillich and Shayu. So an important point here algorithmically is that if you can solve the bounded distance decoding problem out to radius r, then you can prepare this state with peaks of radius r. So here's an example if the peaks are Gaussian with radius r, and so the amplitudes are basically negligible outside radius r, which means that the uncomputation problem you need to solve to prepare this superposition really only requires bounded distance decoding out to radius r, and you can just make this state efficiently using a reversible implementation of your classical algorithm that does the bounded distance decoding. And the second point is, if you had this weighted superposition state with radius 1 over r, so the reason I'm switching between r and 1 over r is because that's what happens when you take the Fourier transform. The radius of your weighting envelope is reciprocal to the radius of the peaks that you make on the dual side. So anyway, if you had this state and you measured, you would sample from points on this lattice, and they'd be preferentially the short lattice vectors. And so that's some kind of optimization. At least you could view it as such. And it turns out that in the lattice case in Rn, this will also be a Gaussian weighting function. So one thing you could try to do with this is make a quantum reduction from the problem of finding short vectors to the problem of doing bounded distance decoding on the dual. So the larger radius out to which you can do bounded distance decoding on the dual, that makes the radius on the primal smaller, and therefore the vectors that you sample become shorter. So the further out you can decode, the stronger approximation you can get to your optimization problem. And, well, if bounded distance decoding out to very large radius, sufficiently large radius becomes NP hard, finding short vectors out to down to sufficiently small radius is NP hard. And so you have to think carefully to determine whether this quantum reduction ever actually buys you anything, because you're trading one hard problem for another, and there's some relation between the hardness of the two. To get a tighter approximation, you need to solve a harder decoding problem. And so, as I mentioned, no exponential quantum algorithmic speedups were found with generic lattices and standard decoders this way. But more recently, in the past few years, there have been some algorithmic successes from considering lattices or codes that are more structured and using decoding methods that are more fancy. And the DQI algorithm, although we don't necessarily cast it this way, and it's not the way we originally thought about it, in retrospect, it can be seen as essentially an example of this. And the way to view it in terms of the prior slide is the simplest version of DQI basically amounts to solving a nearest code word problem. So, and that's just a slight generalization of what's in this picture, because here we have an envelope function on the left-hand side that's centered at the origin, which samples short vectors. But you could have an envelope function centered at some target vector v, and then you'll preferentially sample from lattice vectors that are close to v. And to make that state, you just make the same kind of superposition over peaks that we show on the right-hand side by bounded distance decoding. We just need some extra phases on there to make it its Fourier transform centered at v instead of at the origin. And that's sort of roughly speaking, the essential geometric picture behind the simplest case of decoded quantum interferometry. Okay, so what do we specifically consider? So we consider lattices over finite fields, say the simplest case is if they're prime, so integers mod p. although I guess that's in the eye of the beholder, but I consider those ones the simplest. And such lattices are called linear codes. And instead of optimizing for short vectors, we optimize for more general objectives, which include vectors near to a specific target point as kind of the simplest special case. And we don't look at generic codes, sort of arbitrary generic matrices B that are the generator matrices of these codes. We look at more special ones. And the two cases we consider are first, well, what if the generator matrix is sparse? And the second is, what if the generator matrix has some algebraic structure? Specifically, it's a Vandermonde matrix. And these are not kind of arbitrary structure we impose on the problems. They arise from natural and well-studied optimization problems. So it turns out that if you take the Max-XORSAT problem and express it in the form of a nearest code word problem, then it will have a sparse generator matrix. And it also turns out that if you start with a problem of polynomial regression and express it as sort of a generalized problem about codes or lattices, then it gives you a generator matrix. Well, it gives you a parity check matrix for the dual that's a Vandermonde matrix. And so now I'll go through these two examples one by one. Basically, the point of this structure is that once you have it, it makes the bounded distance decoding problem on the dual much easier to solve out to larger radius. And that's what gives us good results from this quantum reduction. Okay. So Max-XORSAT is the following problem. We have a non-square matrix, mod 2, F, B, and then we have some target vector, V, and we have a list of linear constraints, which are bi.x equals vi, where bi is the ith row of B, x is our vector of decision variables that we're trying to optimize over. So one way you could think of this is you have an overdetermined system of linear equations, mod 2, bx equals v. You can't solve all of them, but you want to solve as many as you can. And in contrast to the square matrix version of this, which you could just solve by Gaussian elimination, the overdetermined version is NP-hard. And you could also view this as a nearest code word problem. It's not even just analogous to a nearest code word problem, it is a nearest code word problem. So we can let C be the code, which is the set of bit strings in the image of B, and we want to find the code word with smallest Hamming distance from the target vector V. And in the approximate case, it's not necessarily smallest, but just small Hamming distance from V. So now we can think back to the picture we had a few slides ago about lattice problems. We have an understanding about how to reduce the approximate nearest code word problem on a given code C via Hadamard transform to a bounded distance decoding problem on the dual code C perp. And, well, as we've mentioned, these are both NP-hard problems, so it's not obvious that this is a helpful thing to do. And to understand whether this is a helpful thing to do, we have to think concretely about the parameters involved. So our original problem is to find a code word in the code C that matches S bits of an arbitrary target string. So the exact, as S becomes larger, we're trying to get closer to our target string and the problem becomes harder. And DQI via a Hadamard transform reduces this to a bounded distance decoding problem where given a string that's promised to be within radius L, of, and by that I mean Hamming radius L of the code C perp, we want to find the nearest code word in C perp. And so these are NP hard if S is big or L is small, respectively. And they become sort of continuously easier as you shrink S or grow L. So this really leaves two questions. The first is, for a given L, what is the largest achievable S via DQI? And that's really a question about Fourier analysis. It's just saying, basically, as a function of how large our little peaks are around the dual code, how wide will the envelope function be on the primal code if we make an optimal choice of peak shape? But the second question is, what structure in the code C allows C perp to be decoded efficiently out to large L? And that's more of a computer science question, which has to do with the specifics of these codes and how classical algorithms perform at decoding them. So next I'll address these questions one by one. So here's the answer to question 1 for the case of when we're working mod 2. So L is the number of errors that you can correct in bounded distance decoding. It's sort of this radius out to which you can decode. And correspondingly, the radius of these little peaks you can make, shown in the top picture. M is the total number of constraints in our original Max-XORSAT problems. And S is the number of constraints that we are able to satisfy. And so this envelope function we get on C defines some probability distribution over bit strings, and we can figure out an expression for what's the expected number of constraints that are satisfied when we sample from that distribution. And then we can optimize over all possible peak shapes of radius L on the dual side and find out what's the best value of expected S that we can achieve. And it turns out to be given by this formula, at least asymptotically in the limit of large M. We also have a formula for finite M, which is more complicated. And so we call this the semicircle law. And this really answers the first question once and for all. And it's a matter of Fourier analysis to derive this. And this formula is really a key tool for us now, because what we can do is we can consider some class of problems. We can then figure out what the dual lattice or code is to those optimization problems. And then we can ask what radius out to which can we solve bounded distance decoding. We can study that either empirically by computer experiments with heuristic decoders, or we can just harvest theorems from the coding literature. And whatever we find, we just plug it in as our value of L into this formula. And then that tells us how good of an optimizer we have, which we can then compare either against proven results for classical optimizers or against empirical performance of classical optimization heuristics. So even though, of course, we don't have quantum computers large enough to run experiments, we can still take, if we want to, a very experimental approach towards quantum optimization. We can run decoders at 50,000, 100,000 variables, no problem, and run our classical heuristics on the dual problems with very large problem sizes and just see how they compare, benchmark them against each other on an instance by instance basis. So that's a very interesting thing that's enabled by this semicircle law. So now we can move on to the second question, which is what structure in the code C enables efficient decoding out to large radius L, and thereby gives us a large value of the expected number of satisfied constraints. And ideally, this should be on a problem where finding a large number of satisfied constraints classically is hard. And can we find quantum advantage? So we address this with two examples. One is where the structure is just that B is sparse. And the other one is an algebraic structure, basically that B is Vandermonde. So next I will go through those two examples. But before doing so, let me just illustrate why we call it the semicircle law. It's because if you plot it, it really does plot out a semicircle. That's this dotted line here. And at any finite size behavior, we can also numerically compute in polynomial time what the exact behavior is, rather than relying on the asymptotics if we need to. Okay, so the first example is Max-XORSAT. So as I've mentioned, we have an overdetermined system of equations mod 2. We want to satisfy as many as we can. And one way that this problem might be restricted is that each variable is contained in at most d constraints, where d might be a constant. And this is a very common occurrence in the study of Max-XORSAT. It's been studied in many prior papers. And so, but another way of looking at it is that this matrix B is d-sparse. There's at most d non-zero entries in any column of B. And so what happens then is, if you look at what that implies about C, it means that C is a low-density generator matrix code, LDGM code. And if you do a Google search for LDGM codes, you will get some hits, but not very many. And that's because these are really not good codes. They have terrible distance. Nobody uses them for error correction, and for good reason. But the dual code, C-perp, has a low-density parity check matrix. Remember, C and C-perp are obtained by swapping the role of parity check matrix versus generator matrix. And low-density parity check matrix codes are excellent codes. They have great distance, and they have very efficient classical decoders that can decode out to large numbers of errors, i.e. large radius L. And there's a good understanding of what radius they can decode out to. In some sort of average case instances, there are sort of analytic semi-rigorous derivations of this. You don't have to rely entirely on empirical computer experiments to know the decoding performance. And so that was kind of very enticing to us, because as we know from the semicircle law, if we can decode up to large radius, that gives us the larger radius we can decode out to, the better approximation we can get to the original optimization problem. And so, as I mentioned, we can just sort of run experiments now. We can choose some ensemble of instances. We test classical optimizers on those instances to see what we need to beat. We test classical decoders on the dual or use theorems about them. That tells us what radius we can decode out to. We feed that into the semicircle law that gives us a corresponding expected number of constraints satisfied by the quantum algorithm. And we just compare that against what we saw from the classical optimizers. And if classical wins, then we go back to the drawing board and either choose a different ensemble of instances or a different set of decoders. Whereas if quantum wins, then we're happy. Although, of course, in practice, really, you go back and test some more additional classical optimizers and really try to make sure you haven't overlooked something. So this is something you can do out to a large number of variables. The experiments plotted in our paper go out to 30,000. And one thing to keep in mind about this is, I think it's a bit, people sometimes ask me like, well, can you get generically quantum speedups for very broad classes of optimization problems? Or can you get speedups for optimization problems that arise in various real-world industrial contexts? And my response is to sort of hold your horses. Like, this has been, even the existence of exponential quantum speedups for optimization has been a very long-standing open question for probably 30 years. And so let's think about the existence questions first. Can we at least find one example where we get quantum speed up? And after that, we can worry about, can we find speedups that are very broad or very industrially well motivated? So here's what we found eventually by doing such experiments. So for sparse matrix B, DQI's decoding problem is LDPC, and the kind of standard decoder for LDPC codes, which is usually the best in practice for most parameter regimes, is called belief propagation. And so in the spirit of the existence question, we tuned the sparsity pattern of an example to intentionally make it as hard as we could for classical optimizers and as easy, as sort of beneficial as it could be for belief propagation, and compared via the semicircle law. And in the end, this way, we were able to find instances where DQI with belief propagation decoding was beating all of the general purpose classical algorithms that we tried. But eventually, and I should really credit Sergei Isakov with this, eventually we were able to find a tailored kind of customized heuristic classically that exploited the specific quirks of these instances to eke out a win over DQI. So what should one conclude from this? I mean, I think that's up to you, but my personal takeaway is that it seems encouraging in the sense that it's not that easy to beat simulated annealing in practice. In a way, we were setting a difficult bar for ourselves because, at least for the average case, there are sort of semi-rigorous, provable results about the performance of belief propagation, and we're holding ourselves to a high bar of competing against classical heuristical, the empirical performance of classical heuristics, which is often much better than anything one can prove. And certainly, one doesn't have to stop with the standard off-the-shelf go-to decoder. I think it's a very interesting set of subsequent research to look at more customized decoders and whether those are able to get DQI to have an outright win instead of only a win against general purpose algorithms. And so I think these results are encouraging enough that I would feel comfortable investing effort in that kind of research. Okay, so that's example one. Now we'll get to example two, which is, to skip to the punchline a little bit, as far as we know, an actual exponential quantum speedup. And so the problem that it applies to is something that we call optimal polynomial intersection, which is a generalization of polynomial regression. And so what this problem is we're given m targets, and we want to intersect as many as possible with a degree n univariate polynomial where n is less than m. And we take all these equations mod p. So we're working over the finite field fp. And n less than m is important because that's what makes this kind of an over-constrained problem. And I should specify what we mean by hitting targets. So of course, in polynomial regression, you're just given like a bunch of points and you want to fit them with a curve. And in this case, since the degree is low, you can't in general fit them exactly. So you might want to hit pretty close. So one version of hitting pretty close would be, well, get within like plus or minus epsilon. And so if we drew a picture of that, we would have like these little yellowish strips would all be line segments. And those would be our plus or minus epsilon line segments around our target points that we want to hit with our polynomial. But optimal polynomial intersection, we consider the general case where these targets could just be arbitrary subsets of FP. They don't have to be little line segments. And this is a very non-convex optimization problem. So it's pretty hard. And furthermore, it's if you think of it in terms of how many variables are involved in each constraint, it's really each constraint involves every variable. So in that sense, it's a very dense optimization problem, which makes it basically useless to try local search heuristics such as simulated annealing and so on. Now, what it turns out is that if our original problem is this optimal polynomial intersection problem, then we can sort of express that as well, if we can use DQI to reduce this to a decoding problem on some object that's dual to what we started with. And the decoding problem we end up with turns out to be decoding of a Reed-Solomon code. And this is somehow a consequence of the algebraic structure intrinsic in the original OPI problem. And that is great news if you end up with a decoding problem on a Reed-Solomon code, because Reed-Solomon codes are basically the best possible codes in almost every way you could hope for, except for one thing, which is that oftentimes people want codes over a binary alphabet, and these are over a mod P alphabet. But in our context, we don't necessarily care about that. And one of the specific ways that these codes are so excellent, along with having a large distance and so on, is that they're very, very good decoding algorithms. In particular, you can decode all the way out to half the code distance using algebraic techniques such as the Berkeley-Massey algorithm, which runs in polynomial time and gives you guaranteed 100% decoding success out to half the code distance, which is a very large distance. So what that means in DQI is we get a very large radius L and consequently a very strong approximation ratio. And we had to compare this to classical algorithms. This problem has been studied before, at least special cases of OPI have been studied before. The coding theorists would call this the list recovery problem for Reed-Solomon codes. Turns out that if you have a Reed-Solomon code, its dual is also Reed-Solomon. So the original primal problem and our decoding are both Reed-Solomon codes, just slightly different ones. But their main distinction that allows us to gain advantage is that we're switching between sort of an approximate nearest code word problem and a bounded distance decoding problem. And the bounded distance decoding problem just ends up being more advantageous when we compare the two via the semicircle law. And also, this problem has been studied in the cryptography literature, where they call it noisy polynomial reconstruction. And the regime we look at has codes that are very low rate, and these list size are very large. So this sort of plus or minus epsilon. If it was the regression case, it's a pretty big epsilon. And in these cases, the known algebraic algorithms for this problem that have been published in the literature, such as the Guruswamy-Sudan algorithm, seem to just break down. They don't apply. And so that just leaves classical heuristics to compete against, as far as we know. And there are good theoretical reasons which are confirmed by our computer experiments, which say that simulated annealing and all other local search heuristics will actually, in the limit of large problem size, converge to achieving no better than random chance. And that just leaves a very naive heuristic to compare against, which is basically throw away the extra constraints until the problem is no longer overdetermined and solve what's left. And that just gives you 55% success in this example that we looked at. Whereas DQI got 0.7179, which is a half plus square root of 19 over 20. And so as far as we can tell, we're achieving an approximation ratio in polynomial time by DQI that cannot be achieved by any polynomial time classical algorithm that we have been able to find in the literature or devise for ourselves. And of course, one point of advertising these results in talks like this is to invite classical experts to see if they can outcompete this with classical algorithms. that's how we'll finally, resolve these questions, only through such kind of scrutiny. Okay, so in my last 10 minutes or so, I'd like to give a different perspective on DQI, which is really the one that we use in our paper and the one that we used originally to conceive of DQI, and which is a little bit different from the geometric picture that I gave at the beginning, and I think gives kind of a complementary perspective. So, and it also gives you sort of two chances. Maybe that's good pedagogy, I don't know. But so anyone who didn't follow the geometric point of view might prefer the algebraic point of view, and vice versa. All right, so here's the polynomial perspective. So we have some cost function, f of x, and we have any polynomial, univariate polynomial p of degree L. And what we ultimately do with DQI is prepare a superposition over symbol strings x, all possible symbol strings x. These are decision variables. And the amplitude on a given string is p of f of x. And so as a simple example, you could imagine that this multivariate polynomial p is just p of f equals f to the L. It's just a single monomial. And so then in the amplitudes, we'd have f to the L. And that's a pretty good thing to have. So then when we measure, according to Born's rule, we would obtain a given string with probability proportional to the cost function value raised to the 2L power. And so that biases us towards strings where this cost function has large magnitude. And so that's giving us it's sampling from good strings that are good approximations to the optimum. And this is really in detail how we think about this state that I showed with the envelope function on the code that's sort of biasing us towards short lattice vectors or whatever, but this is sort of more general. And so it turns out that DQI is efficient if this dual code C-perp can be decoded efficiently out to L errors. So the number of errors we can decode determines the maximum degree of the polynomial that we can use. So we can decode to larger errors. We can have a stronger bias toward good bit strings, as you can see from this example with f to the L. Bigger L gives you a stronger bias, but requires solving a harder decoding problem. So how does the algorithm actually work? That's one thing I've neglected to tell you so far in this lecture about the algorithm. Now let me give you a sketch of that in the simplest example, which was the Max-XORSAT example. How it works in the OPI example and is, a generalization of the same ideas, but more complicated technical details. Okay, so recall the Max-XORSAT problem. Bx equals v. The constraints correspond to the m rows of b. bi dot x equals vi. We try to satisfy as many as possible of those linear equations. And so we can rewrite a Max-XORSAT cost function in a suggestive form. So we can write f of x equals sum over I from 1 to m of -1 to the bi dot x plus vi. And we can see that if bi dot x, remember this is mod 2, so these things are always going to equal 0 or 1. If bi dot x equals vi, then we have -1 to the 0 or 2, which is the same thing, is +1. So if it's satisfied, we get a +1. If it's unsatisfied, then bi dot x plus vi, mod 2 is 1. And so we'll have a minus sign. So this cost function tallies up the number of satisfied constraints minus the number of unsatisfied constraints. And so then let's think about, well, what's the Hadamard transform of this function? Well, you can read it off just by staring at it. It has amplitude -1 to the vi on wave vector bi, and everywhere else we have amplitude 0. So there's only the number of non-zero entries in this Hadamard spectrum is just m, the number of constraints. And so if we wanted to make the DQI state for the linear polynomial, that would be very simple to do. We just create a superposition over these m bit strings, put the appropriate minus signs on some of them, and then do a Hadamard transform. And so that's something we can do very efficiently. It's very easy. And so that's, in a sense, like the simplest example of a DQI algorithm. It's just not very interesting because when we bias according to the first power of the cost function, it doesn't really get you very far on your optimization problem. So let's next think about what we would do if we want higher powers of the cost function. So let's first write down what the square of the cost function is. So we can see if we square the cost function, we'll get all possible cross terms. And when we take the product of a cross term, the exponents add. So now our new wave vectors are like the various possible sums, bi plus bj. And we have the various possible sums, vi plus vj also. And so we can rewrite this in terms of, well, we can write this as the sum over all bit strings of Hamming weight 2 of -1 to the yb. Yb will be the sum of two rows of b, and y dot v will be the sum of the corresponding two entries of v. And so if we can make that state, we would Hadamard transform it, and we get f squared into the amplitudes, basically. There's a small technical detail I'm sweeping under the rug for simplicity, but that's the idea. And okay, so you might guess, and if you did, you would be correct, that if you create the sum over all bit strings of Hamming weight L and put -1 to the y dot v times yb as your initial state instead of just Hamming weight 2, and took the Hadamard transform of that, you get f to the L into the amplitudes. So that shows, gives us the idea behind DQI. So it might be hard to produce this state, but we can always produce the uniform superposition over all bit strings of Hamming weight L. So that's not too hard. Those are called Dickey states, and there's known, due to some application in physics, and there's known quantum circuits for making them. Once you have that, adding a second register with y times b, that's easy also because you can just do the matrix multiplication reversibly. Adding the phases is also easy. But then the last step is you have to get rid of this extra register y. And once you uncompute it, then you have what you want. You Hadamard transform, you get your state. So uncomputing y is really the hard part. And that's because b is non-square. You can't just do linear algebra to determine y from yb. That's a underdetermined problem. But remember, we have the constraint that the Hamming weight of y is L. And so from yb, computing y with the constraint that the Hamming weight of y is L is exactly the syndrome decoding problem for the code whose parity check matrix is B. So we think of y here as the errors and the string yb as the syndrome, and B as the parity check matrix. So if you're familiar with decoding, this will be something you already know. And if you're unfamiliar with decoding, this will be something that's probably impossible to follow in real time when someone's just saying it in 30 seconds. But if so, you can just take that on faith or think it through later. So now I'd like to sort of wrap up. One thing before I do I'd like to mention is that here I've used Max-XORSAT as an example, but we didn't have to choose Max-XORSAT. Max-XORSAT is especially simple because each constraint contributes exactly one term in the Fourier spectrum of the cost function. But if you have any arbitrary constraint, it doesn't have to be some XORSAT type constraint. If it involves only k bits, then that will contribute at most 2 to the k terms in the Fourier spectrum. And so if you have some other problem like Max-KSAT with constant k, vertex coloring on constant degree graphs, whatever, and you look at the Fourier spectrum of such a problem, then the number of non-zero coefficients will still just be linear in the number of constraints, as long as k is a constant. And so the same ideas apply. It's not really specific to Max-XORSAT. That's just the cleanest example. and most efficient example. Okay, so now I think there are really 10 slides worth of open questions that we could look at, but maybe we'll get into those a little bit in the discussion session. But I'll highlight a few. So one thing that you can see from this algebraic perspective in terms of the polynomials is that you could view DQI as a state preparation method. We have some polynomial, and we want to prepare, P of f as our amplitudes in some quantum state. And maybe that's useful as an initial step for some other quantum algorithm that uses that quantum state for something. But also another thing you notice about these states is they have a nice property, which is that when you sample, the probability of getting a given string depends only on the cost function of that string. So it's unbiased within the set of strings of a given cost function value, which is something that most classical heuristics like simulated annealing and so on don't have that guarantee in the regime under which they're run in practice. And so that might allow you to solve some interesting sampling or approximate counting problems that could potentially be hard classically. So that's another direction that one could consider. And of course, one of the big open questions is, can we push harder on the decoders or find a more suitable class ensemble of instances where instead of just getting speed up over simulated annealing and some other general purpose algorithms, we just get an unconditional, well, let me phrase this carefully. We get a speed up that seems to hold up against every classical algorithm we can think of. And so maybe you could look at some other decoders like linear program decoders or neural decoders. These might actually perform a bit better on parity check matrices that are denser, which could help because those are the cases that are harder for the optimizers on the dual problems. And well, of course, I want to lay down the gauntlet here. Can any classical computer scientists find a polynomial time classical algorithm that matches DQI on the OPI problem? I hope that the answer is no, but if the answer is yes, of course, we want to know about it. And I think this polynomial regression problem hints at maybe a broader class of speedups for other algebraic problems that could be attacked with DQI. We already know how to generalize this to multivariate polynomial regression and get some interesting results there. They're not out yet, but I think hopefully maybe it's the tip of some kind of iceberg. So that has to be explored, I think. And there's also more complexity theoretical type questions like, for example, as far as we can tell, this algorithm has nothing to do really with a abelian hidden subgroup. And so it's kind of unusual to find a quantum speedup, an exponential quantum speedup for some problem other than physics simulation, which is based on anything other than a abelian hidden subgroup. But we also don't know for sure that this OPI problem couldn't be reduced in polynomial time to a abelian hidden subgroup. In fact, my guess is the answer is no. One of my co-authors, Mary Wooters, guesses that the answer is yes, because she's aware of some connections, at least loose connections between discrete logs and Reed-Solomon code decoding problems. But that's sort of, I think, a pretty interesting theoretical question. And also there's a question of the complexity theory behind all this. These approximation problems, can we show that they're in NP, intersect co-NP, and so on. And so I think I'll stop here and thank all of you for your attention and thank my collaborators who have been absolutely crucial to this work. And especially I'd like to call out Noah Shuddy, who's the co-corresponding author of this work.
Great. Well, thanks, Stephen. That was a fabulous talk. Let's see if there are any questions before we move on to the panel. I think Dave Bacon has a question. Dave, let's see.
accidentally just raised my hand. So.
Sorry, before we move on, Stephen, while we're waiting for other questions, you did, I guess, implicitly address it in the context of the polynomial formulation, but can you, is there something at a high level you can say about incorporating phases that, as you must, in terms of this bounded distance decoding, you must deal with phases there as well if you're trying to be close to some point that you don't quite know?
Yes, so there's two comments about phases. So the first is, if you think about the geometric picture and you want to understand the phases, basically you can understand it in terms of the convolution theorem, or even a more elementary fact that if you take some function and you shift it, and you take the Fourier transform of that, then its Fourier transform will be the same as the unshifted version, except with extra phases across it. And so that's why the phases are there in some sense, because we're solving sort of a nearest problem to this target vector v, at least in the Max-XORSAT case, rather than a shortest code word problem. And so, but the other thing to say about phases is that how do they affect the decoding problem? So if you are using a reversible implementation of a classical decoding algorithm like belief propagation or the Berkeley-Massey algorithm or whatever, then the phases actually make no difference, because you're sort of dealing with one branch of the wave function at a time, so to speak, and the phases just don't matter. It's as if you had a classical distribution over errors. Now, there are advantages you can try to exploit from the fact that these errors are actually in coherent superposition rather than being in probabilistic mixture. Information theoretically, that is indeed advantageous in this case. And there are some very interesting algorithms for solving this problem. So in particular, there's some papers by Joe Rennis and collaborators where they introduced something called BPQM, belief propagation with quantum messages, that addresses basically exactly the right kind of problem that we need for DQI. And there the phases are important. But it turns out that it's possible to sort of fiddle with the algorithm and put the phases in sort of at a later stage, and you can avoid worrying about them, and you can make your reduction down to exactly the problem that BPQM addresses. So I think that's a very interesting thing that we're still exploring. BPQM is unfortunately harder to analyze than classical belief propagation, but it might perform better and might push DQI over the top for some class of instances that don't have algebraic structure, which potentially.
Great.
Stephen, we have some questions on the Q&A. I can read the first one for you. It asks why the Yamakawa-Zhandry paper is not enough as a strong evidence for an exponential speedup for optimization problems.
Yeah, so it could be cast that way. First of all, the Yamakawa-Zhandry paper, it's a very exciting result. And in a way, so you could view DQI as sort of like a relaxation of the Yamakawa-Zhandry algorithm, in the sense that the Yamakawa-Zhandry algorithm, in the case where it's possible to satisfy all the constraints, it will do so. So it's more like solving a problem that's more like SAT rather than Max-XORSAT. And DQI uses sort of similar techniques to Yamakawa-Zhandry, but sort of relaxes to finding approximate solutions instead of exact solutions. And the other thing that's different is that, so the Yamakawa-Zhandry problem operates in the case where the finite field is exponentially large, and these list sizes that are, or rather you could think of them as the truth tables of the constraints, are exponentially large. And so they're not explicitly known to you. They're given by either random oracles or by hash functions, whereas we were looking at the regime where the truth tables of the constraints are just polynomially sized truth tables that are given to you explicitly, which I think is a little bit more towards the end of the spectrum of more typical industrial optimization problems.
Thank you. Here's another one. You mentioned the sparsity and the algebraic structure of these matrices B, which help with the decoding. Shima is asking whether there is any other known structure that, other than those coming from optimization problems with easy decoding.
Well, so it's a good question. I mean, one way you can approach it is by going backwards. So you could just look at various codes that are known to have good decoders and kind of ask one by one, if you think about what are the problems that are dual to these decoding problems via Fourier transform, are they problems that seem natural or interesting in any way? And actually, that's how we ended up with this OPI problem. We didn't start and set out like, oh, let's try to solve polynomial regression problems with a quantum computer. It was more born out of frustration where we originally wanted to, I originally was hoping to solve, get exponential speed up on Max-XORSAT problems. And that was looking like kind of a slog. And so just to sort of make sure that the algorithm was interesting, the quantum reduction was interesting at all, I wanted to check, like, could we at least construct some example, no matter how arbitrary or unnatural, where it actually gives apparently an exponential speed up, to just sort of like as a sanity check to see that we're onto something, that it's not just trivially dequantizable and so on. And so that's when we plugged in Reed-Solomon codes as our dual code. And it was only later that Noah noticed, like, hey, you know what? The thing that is dual to this actually is a natural problem. And that to me was just a miraculous thing that fell into our lap, or well, into my lap via Noah's insight. So maybe you could repeat that with some other class of codes. If you do that with Reed-Muller codes, you get back multivariate regression. So that's one we already know. But there's all sorts of interesting algebraic geometry codes and GAPA codes and this and that, and they have all sorts of intricate structures. So I think it's not implausible at all that the problems dual to them could be intrinsically interesting and well motivated if you look at them the right way.
Great, thank you. Eli, would you like to speak?
Can you hear me?
Yes.
Okay, so artificial intelligence is also an optimization problem. Can you imagine something in quantum computing that could possibly help?
Well, it's so certainly regression problems can be kind of motivated from machine learning applications. Now, these specific ones we're looking at are regression problems over finite fields, which maybe is a little bit less natural in that context. But you could consider also ones in the continuum. And so then it goes back a little bit more closely related to the lattice papers rather than the code papers that we're writing. The lattice papers from the early 2000s were not thinking about finite fields. Yeah, I guess I would say we don't know, but like that's, if I was going to try to look, that's probably where I would look.
Thank you.
Great. Let's move on to the panel if we can get the video spinned for the panelists. Okay, so let me introduce them as they are being pinned up. Great to have Ronald de Wolf here from CWI and University of Amsterdam. by way of, he was once a postdoc at Berkeley, which we remember fondly. Ronald works on quantum complexity theory, and he's actually, one of the things that he's done, which is quite wonderful, is this work on the quantum method, ways of proving classical results using quantum techniques. But he's also worked on optimization and error correcting codes and theoretical machine learning. We have John Wright from UC Berkeley. John has done a lot of beautiful work on tomography, and of course, this, you know, I'm sure you've heard of his work on QIP star equal to RE, which is truly spectacular. And then it's great to have Mark Zhandry here, who's at NTT Research, but will soon join Stanford, I think next year. Mark has, I think it's clear he really laid the foundations of quantum resistant cryptography. You know, that once you have post-quantum crypto, you still have to think about how quantum primitives, how protocols have to be secure against quantum computers. And of course, he did the Yamakava-Zhandry quantum advantage without structure, which is very intimately related to today's topic. So thanks again for being on the panel, and we'll start with comments from the panelists about the talk. In any order, Ronald, would you like to start first?
Yeah, I can start. Thanks. Yeah, thanks, Stephen, for a very nice talk. I was happy to see the two different perspectives also. So if you look at the field of sort of quantum optimization algorithms, there are like two big clusters there, and then there's a few outliers. I would say the two big clusters are things like adiabatic, QAOA, annealing, etc., which are usually kind of heuristic, sometimes variational. In special cases, maybe you can analyze them, but generally it's more of a heuristic. And on the other hand, there's a whole class of algorithms, often based on Grover, that give you like polynomial speedups for things like linear programming, semi-definite programming, some regression problems, etc. But they suffer from the fact that they often need QRAM assumptions, and they, like quadratic speedups, are not that great anyway. And then there's a few outliers, which includes, for instance, the tensor PCA stuff by Hastings and follow-ups. And now also your work, and I think this is very interesting, and I sort of like optimistically hope that your stuff is also going to grow into another cluster of maybe like super polynomial speedups without funny QRAM assumptions. I had a few questions during the talk. Maybe I can ask those now. Is that okay, Umesh?
Yeah, please.
So one is about sort of evidence for classical hardness of some of these approximation problems. There was this paper in, I think, Stock 2008 by Prasad Raghavendra, who showed that for basically every conceivable constraint satisfaction problem, he could write down an STP, which, assuming the unique games conjecture, would get the optimal approximation ratio. I don't think you cite this paper in yours, so I wonder, are you aware of it? Can you use it to get, let's say, the optimal approximation ratios achievable by classical algorithms, by kind of digging into Raghavendra's paper and extracting from the STP the best that classical algorithms could do?
So we haven't done that. Yeah, it's a great suggestion. I don't have much comment on that right now, but certainly I'd love to receive that reference and take a look.
Yeah, it was one of the best papers in Stock 2008. It's easy to find it.
Oh, great. So I know that I'm not sure how related this is, but one of my co-authors, Robbie King, has been starting to think about what can the sum of squares hierarchy tell us in terms of a more theoretical foundation for hardness at different levels of approximation. But I'm not sure if what he's looking at relates closely to what you've just suggested now.
Yeah,
It's
maybe I
probably
can say
because it includes a sequence of SDPs. for
maybe I
example.
can say one thing about this, which is that I think for the Max K XOR problem that's considered in this work, I mean the best classical algorithm, if you just look at K XOR, is just to flip random coins and choose a random assignment, and Prasad's algorithm matches that. But in this work, they consider like a stronger constraint on the instance, which is that it's a bounded degree instance. So every variable only appears in at most like D clauses, where D is some parameter. And for these sorts of instances, I don't think Prasad's results apply. So he considers in his instances, there's like no bound on the number of clauses that variables need to sit in. And so actually for the best algorithm, at least the best classical algorithm that's known, that came out in 2014. I was one of the co-authors on it. It's like it has like 20 authors or something like this. And it was the work that was done in response to one of the original QAOA papers. And that algorithm, it's very different than any like Raghavendra style SDP. It doesn't use the Gomez-Williamson SDP at all. It just assigns some variables at random and then picks the other ones greedily.
Yeah, so I should mention we did implement your algorithm and experimented with it. So in those tables I showed, that one was what we referred to as advarand, which is a name that we sort of copied from your paper.
Yeah, I looked through this before. I didn't even know we called it advarand. So the whole time I was reading, I was like, what algorithm is this? Anyway, sorry, Ronald.
Yeah, so let me sort of rephrase my question. Like, what is the best evidence for hardness that you have for these problems, especially the OPI one?
So I think the OPI problem, I have a strong, well, I guess intuition is what it is that the only really credible classical competing algorithms are ones that very specifically exploit the algebraic structure of the problem. And because it's just such a dense and non-convex problem that I think sort of general purpose heuristics will have no chance. And so what we mainly did was we scoured the literature for all the algorithms for this kind of problem that we could find and just surveyed a bunch of experts from the coding theory, that sort of algebraic coding community. So Mary Wooters was our main go-to person who is a co-author, and she also kind of consulted her colleagues, and we just harvested all the kind of list decoding algorithms for algebraic codes that we could find and just tested them one by one. So that was our due diligence. But we don't have any like more theoretical foundations. It's more just a matter like crypto style, like, well, try some attacks. Well, maybe I shouldn't put it that way, but basically we tried all the attacks that we could find and analyzed them and implemented them to just as sanity checks on our analysis, and that's really the status of it.
Fair enough. And then another question that I have. So in the paper, you give this polynomial perspective that you ended with. I wanted to ask, like, where's the polynomial in the geometric picture where you go back and forth between the two peak landscapes?
Yes. So in our paper, so there's actually two ways of doing DQI, only one of which we describe in our paper. It was plenty long enough already. And so you basically can do what I call message space DQI and code space DQI. So what we have in our paper is what I would call message space DQI, because we have this non-square matrix. On one side, its dimension is the number of variables. On the other side, its dimension is the number of constraints. And so if you think of that as the generator matrix for a code, you're taking these short messages and encoding them into these long code words. And so our number of qubits that we act on is like the message side, the small side. And so then the relation to the geometric picture becomes not so clear, because we're actually at the end getting a superposition over all possible assignments to these bits. And so there's no, like, it's not like it looks like a superposition over a code of these evenly spaced bit strings. But you could work on the other side, where you're really operating on the code. And from that point of view, it really matches to this lattice point of view. And so our choice of polynomial is basically of degree L polynomial corresponds to the choice of like these peak shapes. So we have all these possible peaks shapes of radius L, which corresponds to all the choice of the coefficients in your degree L polynomial. And there's kind of a, there's like a bijective mapping between those two parameterizations of your choices.
Mm-hmm.
Thanks. There's other questions that I could ask, but maybe it's good to move on to the others.
Do you want to pick up where you left off, John?
Sure. Yeah, so thanks for the talk. Yeah, I spent some time this morning reading through the paper, or as much as I could, in the time I had. And one thing I liked about it is like, at least for me, I come from like a very computer sciencey background, and there have been like previous, quantum approximation algorithms that rely on a lot of physics intuition, which somehow my brain is just like not wired to be able to understand physics at all. But this paper, it was like this approach. It's very it's something that I feel is like very computer sciencey. It's very understandable to me, and I thought the algorithm was very elegant. Yeah, I enjoyed reading the paper. I like the ideas behind the algorithm. Hope it works out. Yeah. So I guess my background or my bias is typically when I see like I've claimed, quantum improvement for some optimization problem like exponential speedup, especially ones of like the Max-XOR flavor. My bias is that I feel like, classical algorithms are very powerful. And so that's kind of what I expect when one is looking at, let's say, bounded degree Max-XOR. This is kind of what happened previously when like the QAO papers came out. They gave, improved algorithm for bounded degree Max-XOR. And it kind of inspired, us classical people at the time to go and find even better classical algorithms, which then inspired the QAOA folks to find matching quantum algorithms. But the end result was that I think for that problem, it looks like basically classical is kind of the best you could hope for. So it's like nearly matching with the PCP-based lower bounds. And I guess you guys ran simulations for this and found that like for maybe the Gallagher's distribution over instances, this algorithm from our paper does kind of outperform the DQI algorithm. But then for like another tailored instance that you guys looked at, with tailored degrees, the DQI algorithm outperforms one from our paper. Yeah, and that one, well, I guess then you guys came up with an algorithm, a classical algorithm that beats DQI. But yeah, my suspicion is that for problems like this, which have been studied a lot in the classical literature, it just seems like the classical algorithms are already very, very strong. I'd be more hopeful about this OPI problem, so this optimal polynomial. I forget the I.
Yeah,
First off, I
intersection.
think intersection. Yeah, I think it's a very natural problem. Like again, a very elegant problem. And so even if it turns out that like there's a classical algorithm that beats it, I think it's just worth posing the question. And this one, I think for me, I'd really like to see classical people take a stab at it and see what can, well, you had Mary Wooders on the paper, but what can the Venkat-Goswamis of the world do with this challenge? And I really hope that they, use this paper as inspiration to begin, I guess, a classical quantum arms race. So actually, I wanted to follow up a question that, since Ronald asked you, what evidence and who did you ask? So what are Mary's beliefs? Does she believe that this is potentially actually a classically hard problem, the OPI problem?
Yes. Of course, it always is subject to the possibility of being shot down by some clever innovations.
Yeah.
But I think at a minimum, she felt that kind of standard known techniques couldn't do it, and there was no obvious classical attack. So she felt it was quite plausible that it's beyond the reach of classical computing, but of course you never know.
Okay, I mean that's compelling enough for me. I think
It's
that's
interesting.
strong
Your
evidence.
intuition, I spoke to Scott Aronson about this a few weeks ago. His intuition was very similar to yours. He felt that for these kind of random sparse problems, he's like, yeah, guys, knock yourself out. But I think he felt it was unlikely that one could find a genuine exponential quantum speed up there, whereas he was much more optimistic that first of all, that the speed up for OPI would hold up to scrutiny, and furthermore, that it could be generalized to a number of other related problems. Although, some of my co-authors are, on the other hand, more optimistic still about the random sparse things, especially if you add some kind of additional element that's not algebraic structure, such as like planted solutions or things like this. And so we definitely haven't given up on that.
I guess the one other question I would have right now is another thing you can look at is just like sampling from the output distribution of the DQI algorithm. Even in the case when I guess like you're not looking at a high degree polynomial, but your coefficient is just f of x. Can that be done? Is that just like rejection sampling or something?
Yes. So for f of x, I'm pretty sure you can do it classically, because basically you have the weight distribution of the code, which looks binomial, and it's sort of fighting against the countervailing factor, which in that case would be f squared. And so that should be doable with rejection sampling.
I see. So is it like for constant degree, you can probably do it classically, but then there's some minimum degree at which it's not obvious?
Yeah, I think I would have to go back to my notes to see the specifics, but I think generally speaking, the interesting case is where the degree is linear in the problem size, say linear in the number of constraints.
Okay, thanks. Maybe that's all my questions for now.
And that sort of corresponds to the dual being a good code, in the sense of having distance and decodability that go linearly with the block length of the code.
Great. Thanks, John. Mark, really looking forward to your comments.
Hi. Yeah, so very, very nice talk. Yeah, I guess the one thought I was having was just how, so when Takashi Yamakawa and I had our result, we were advertising it as, oh, hey, look, here's a quantum speed up that doesn't involve period finding. But it still involves quantum Fourier transform at the heart. That's still the core algorithmic technique. And like our work, your work, still the core quantum part of the work is the Fourier transform. And it seems to, like, talking to people outside of the quantum space, that they maybe kind of treat Fourier transforms or period finding as equivalent. But I guess one of the takeaways from this line of work is that the Fourier transform isn't just useful for period finding. It's potentially a lot more powerful. Here's one other little nugget it can achieve algorithmically. But it also raises kind of a interesting question, which is, okay, fine, we've found more uses of Fourier transform, but is this still the main quantum technique that underlies everything we do? So I don't know. I think that's at least for exponential speedups, it seems like Fourier transform is really the core, and not sure that that's the only. Should that be the only thing out there? I don't know. But that was just one thought I was having. And I guess I wanted to also mention just a concrete or like my interpretation of how to answer the first question that you were asked by the audience, which is just so my paper with Takashi, we came up with a contrived problem that allowed us to prove in some sort of model that we actually get an exponential speed up. And maybe what's different here with your work is that it's really a natural problem that you get at the end of the day. And I think that is an important aspect of it, that yeah, sure, we can cook up contrived problems that might have exponential speedups, but here's a really natural one that we hope has an exponential speedup. And yeah, it seems like that is like a clear advantage among others over my paper with Takashi.
Yeah, one thing I could comment is this won't sound like it has to do with what you just said, but actually it does. So I've presented this work to some practitioners from like operations research teams at both Google and Amazon. And in both cases, they had the same comment, which is that, well, for real world optimization problems, you usually care about constrained optimization. And but an interesting thing is that if you sort of take the DQI way of doing things and kind of combine it with the Yamakawa-Zhandry way of doing things, there actually is a way to directly incorporate hard constraints into the problem that DQI solves.
Mm-hmm.
So basically, you take the Fourier transform of the indicator function of the constraint and then convolve with it on the dual side. And what it ends up happening is that this ends up being a bit in your code where the bit flip probability is half instead of being some small number, which is L over M. And so basically, then you can ensure that there's actually zero amplitude on the infeasible subspace at the cost of having having higher error rate on some of your bits. And this is very different from like a lot of heuristics where to incorporate constraints, you have to add penalty functions and turn them into soft constraints, which is, I actually worked for a bit doing that kind of applied work. And anytime you have to do that and then tune the penalties, it's really, first of all, tedious, and secondly, often ineffective. So anyway, it seems like there might be an interesting intersection between these very theoretical ideas from your paper and these very applied desires from the operations research people.
Yeah, I guess so. Another question I had, kind of unrelated. So right, so what DQI or what my paper did was like it's map or Regev before us, right? It's mapping one type of problem into another type of problem, and you could try to see what happens when you map NP hard problems. And at least doing it the naive ways that I tried, what you end up getting is you actually map an NP hard problem to a statistically hard problem. And I'm wondering, is that also the case where if you take regimes for your algorithm where the optimization problem is actually known to be NP hard, does that map to, so it presumably maps to a problem that you don't know how to solve, but is it actually a problem that is information theoretically solvable, or do these become also kind of information theoretically unsolvable instances?
Yes, that's a good question. I mean, I think if you have a dense code, so B, let's say your matrix B is chosen by doing a coin flip for every entry, then information theoretically, the decoding problem is no worse than the one for LDPC codes, but algorithmically, it's just vastly more difficult, and also the optimization problem that's dual to it is vastly more difficult. So I think in that case, it's the information theoretic barriers are just way beyond the computational barriers, and they don't coincide at all. But once you get to the sparse examples like Gallagher's ensemble, then it's a tougher call, I think.
I see.
Great.
Can I ask another question?
Sure, please.
So some of these techniques are sort of reminiscent of the branch of post-quantum cryptography that's code-based. Do you think any of these techniques, maybe this is also a question to Mark, can any of these techniques help to attack certain code-based crypto systems?
It's a good question. I don't know if any attacks. You know, if I did, I would certainly say so. But I think maybe the key point is that, again, you're usually thinking about things with algebraic structure, like in Mechelice, you use GAPA codes, or if you're in these lattice-based crypto systems, usually you're using like ideal lattices and things like that. So I think there's something worth thinking through there about do those algebraic structures give you something on the dual that you can exploit to get some better approximations than what you would otherwise have. And you know, if I were to guess, I'd say probably this search would turn up short and that you wouldn't really break anything important. But and also I think it would be pretty hard work because the math involved is very intricate with these complex algebraic structures. But like, absolutely, I think it's worthwhile thinking it through. I don't know if any of the rest of you have more insight than that.
So just to follow up on that, so in those crypto systems, in addition to the algebraic structure, one has to do something else to put in a trapdoor, like a permutation or something. So how would that interact with the algebraic structure?
Yeah, so I mean, it's sort of, I have to remember because it sort of depends. So if you have like a generator matrix, or which is then the parity check matrix of the dual, and you know, if I recall correctly, you sort of obfuscate it by multiplying on one side by an arbitrary invertible matrix, and you multiply on the other side by a permutation matrix. And then, but then when you go to the dual, these things are on the opposite sides. And I think we did sort of investigate this a little bit, and it did seem to kind of cause problems for DQI because the general linear transformation was on the side of the matrix where it really kind of interferes with what you're trying to do in your decoding on the dual. So yeah, I mean, it's not like we haven't thought about this at all. We've thought about it a little bit and gotten a bit stuck. But yeah, who knows?
So a different direction that might be more fruitful, I don't know, is so recently in crypto, very stretched variants of learning parity with noise have become somewhat popular. And in particular, maybe most relevant is there's this thing called sparse LPN, where I forget exactly how it's defined. It's not something I've spent too much time myself looking at. But you know, there are notions of sparseness there, and maybe they can match the notions of sparseness you use in your Max-XOR setting. Could be something to look at.
Yes. Well, I'm glad this meeting's being recorded because I'll go back. I'm not taking notes now, but I can look up all these things later.
We're close to the end of our time, so any final comments, either from the panel or anybody in the audience?
I posted a question on the question and answer button.
Okay, it says, in the practical world, optimization problems tend to be solved by steepest descent, but you compared your approach to simulated annealing, which is rather slow. What if you compared to steepest descent?
Yes, so we did try one thing that we referred to as the greedy algorithm, which is kind of a steepest descent thing where it just flips one bit at a time and checks to see if there's any downhill moves available and just keeps going until it gets stuck. And for these problems, it was it's true that it did run faster than simulated annealing, but it was not able to achieve quite as high of a approximation ratio that simulated annealing was able to achieve. And actually, the interesting thing is, like, we have kind of a heuristic argument about how what approximation ratio all these kinds of algorithms should achieve, which all the algorithms where it's flipping a bit at a time and making just some decision whether to move that way or not. And indeed, both this greedy or steepest descent algorithm and the simulated annealing algorithm in practice match to that prediction pretty well, which is that the approximation ratio you get should look like a half plus constant over root d, where d is the number of constraints that each variable is contained in.
Great. Thanks, Stephen, for that was a fantastic talk, and thank you, Ronald, John, and Mark for really stimulating panel. So next week we'll have Fermi Mars speaking about these recent breakthrough results on pseudorandom unitaries. Okay, so look forward to seeing you then. Thanks.
Thanks. Bye.
Thanks for organizing this, Umesh.
Oh, you're welcome. Thank you.